Good morning and welcome to this first session this morning titled High Energy Performance Buildings. My name is Tamara Bajc. I'm professor at Faculty of Mechanical Engineering, University of Belgrade. And today with me are our distinguished guests, Professor Catalin Lungu. He's president of RIVA and also professor at Technical University of Civil Engineering, Bucharest. And also Professor Milena Blagojević, professor at University of Florence. We are going to start with our first presentation. For each presentation, we have 10 minutes. And also for questions, we will have 5 minutes more. So please keep up with the schedule. First presentation is going to be presented by Professor Catalin Lungu. The title of the presentation is Decarbonization Through Innovation, New Era of the Holistic Certification Schemes for Buildings at Unit at Complex Level. Catalin, please.
Thank you so much for giving me the floor. This presentation will focus, first of all, on few less known figures about EU decarbonization. Then I will enter into some details presenting what is the idea behind this interesting and exciting title, New Era of EPC for Buildings. And finally, of course, I'll present the conclusions and perspectives. First of all, I would like to acknowledge the whole team of the project where we were involved, Smart Living EPC. And I also mentioned the fact that this presentation was already presented during the Brussels summit a few weeks ago. So let me start with the framework in which we are doing our job. So you know probably that the European Commission set in stone, according to the climate law, different targets for the CO2 emissions, for GHG emissions, then for energy consumption, and also for the energy consumed for and from, in fact, renewable sources. I will focus on this slide to GHG emissions, saying that a huge amount of money is meant for investments from different European plans. For example, Next Generation EU Recovery Plan, and then the EU's 7-year budget will finance the very known European Green Deal, which established 3 targets for 2030, for 2040, the intermediate target, and then finally for 2050, when Europe will become, in fact, the first climate neutral continent. And to see where we are, I'll use some data coming from Eurostat in 2022. And according to those data, it is seen that the CO2 equivalent emissions decreased by 32.5% from 1990 in 2022. In parallel, the economy grew by 67%, meaning that these two indicators are decoupled. On the other hand, in 2024, the electric energy was coming from renewable sources in more than 50%. So half of the production was from renewable sources. And at the same time, the wind power exceeded the natural gas power And this is another signal that we are on the good track concerning the targets set by European Commission. On the hand side of the slide, you can see, I hope you see, that in absolute values, the GHG emissions expressed in CO2 equivalent tons per capita were reduced, and there is a small exception which is not very, very important. So the GHG emissions were decreased a lot in the last more than 30 years. And then we are working under the umbrella of several European directives, very important directives. One of the main directive is EPBD, Energy Performance of Buildings Directive. Even if it is maybe one of the main pieces of the puzzle, is not the only one. The puzzle is made by several others directives like Energy Efficiency Directive, Renewable Energy Directive, and so on. So we are acting in a framework where we have many rules, and these rules will guide us to the final goals in 2030, 2040, and 2050. So EPBD, I won't say too much about this directive, but it is important to mention that many new concepts are presented in this directive. One of those concepts, new concepts, is the zero emission building concept. It is a very consistent directive, much more consistent than the previous one, counting around 70 pages with a lot of annexes, a lot of articles. And this directive will be implemented will be transposed firstly, and of course, afterwards implemented in the national legislations. Okay, so now let's go deep a bit, and I'll explain that inside the European project, we proposed a special methodology. So this project is called Smart Living EPC, in which 70 partners and 17 partners and 11 countries are involved. This project is ongoing. It will end next year in June. We have discussed to reach different objectives, and in fact, the main objective is to assess the buildings not only from the energy point of view, but from other point of views. For non-energy point of view, for smart readiness indicator point of view, and also from environmental point of view. And according to our project, the assessment of buildings will not be limited only to the asset assessment, so based only on calculations, but will go beyond this and will also touch here the operational behavior of the buildings on one side. On the other side, we will, and we are, in fact, calculating and assessing not only buildings at single level building, but also at complex level. So we will assess group of buildings. Then I will also explain that this, let's say, procedure for assessment of buildings at single or complex level is divided on different layers. The architecture starts with the data collection layer, gathering data from IFC beam files, for example, also from different audits, technical audits of the building, of the envelope, and of the technical systems. Then it will use external APIs in order to combine different platforms used for gathering data, and data will be also collected from sensors of different devices. The second layer will be the information management layer. So we have to manage somehow all data gathered on the first layer. And for this purpose, it is meant to use the common information exchange modeling. The third layer is the processing layer, including different calculation engines. And adding values to services for buildings. And the final layer will be a demonstration layer. In fact, it is the web platform itself being used by different users, and of course, giving the final results, as I will see in the next slides. So just to see how complex will be the Smart Living EPC assessment platform, I'll introduce this logical scheme. I don't think you see very well, but it is also a scheme allowing us to divide the work among partners. And also, of course, to give some details, I will skip this slide because it's not very visible. Now going deeper into details only for the asset assessment procedure on which the Romanian Building Services Association has been working. So in this, let's say, part of the project, we proposed an interesting methodology combining different groups of indicators. One and the first group is the energy indicators group. So this energy indicators will be calculated according to European standards. Then another group of indicators refer to environmental assessment. And for this, our colleagues propose to use the level indicators, of course, adapting the indicators to the project. Another indicator is the smart readiness indicator. And finally, we have also a group of non-energy indicators. Again, I will show you what are, for example, the non-energy indicators in one of the next slides. So for all these groups of indicators, we established a rating procedure, so giving scores. And of course, trying to put these scores into rating classes. And using a weighting set of indicators, Finally, we can give a class and a score to the buildings, and the same logic was used in order to assess buildings at operational level and to assess also, as I said, group of buildings. So going a bit into details for the energy indicators group, I can say that at the foundation of the calculation engine for energy indicators is a software which we have developed in Romania. It's called ENEC Plus. And this software, in fact, uses the Excel files coming from EPB Center and, of course, coming from EPB set of standards, so the series 52000. So you can see in this table what are the main energy indicators. So we calculated according to the Smart Living EPC assessment procedure the primary energy consumption divided for thermal vector, for electric vector, non-renewable part of the primary energy, and also the renewable part of the energy. Then total primary energy consumption, which is important to calculate the score of the building. And of course, some other indicators which are important not for the assessment, but for some decisions of users and the final beneficiaries, the building energy overall performance class, the renewable energy ratio, and if possible, and if the case, the exported primary energy also divided for the electric vector and the thermal vector. So all these indicators are computed according to EN ISO 52000 series of standards. In the project, in the deliverables, we explained in detail how all the small parts of the calculation procedures are combined, offering in those documents logical schemes and, of course, detailing till the end every calculation for energy indicators. So going more in detail, we tried to solve and to answer to different questions, also keeping this asset assessment method very simple and acceptable at the same time by the users. This is a European project. Of course, we have to deal with users coming from different member states. It's not very easy to harmonize everything from the energy point of view. And that's why we answer to main questions like how to avoid energy classification of buildings and how to harmonize the energy performance assessment. I can tell from the start that this is not possible, but we proposed a solution, as I will explain you immediately. How to give another question, how to give Smart Living EPC scores for the energy assessment procedure. And another question was what would be the dedicated weighting meter for Smart Living EPC energy indicators. And to answer to all these questions, in fact, we have used ideas mentioned in other European projects or European standards. For example, we used that stepped scale to set the limits for energy classes, as it is mentioned in the standard 53003. And then to find the scores according to the energy, to the primary energy consumption, we proposed the same scoring procedure as was proposed for the smart readiness indicator. And according to those ideas, we succeeded to have an assessment of a building, and of course, as I said, for a group of buildings, so having scores and having also classes if needed. Then for the other group of non-energy indicators, we assessed different indicators for visual comfort. We proposed indicators for acoustic comfort, for thermal comfort, and we add to known assessment procedures already studied in other projects, accessibility index rating, so for persons with disabilities access, and for water consumption, also another rating. And we included the earthquake hazard risk in our assessments. And I don't want to forget to mention the fact that for the indoor air quality assessment, we also introduced the radon risk rating. For this group of non-energy indicators, the rating system is based on equal default weighting values, but the weighting values can be also chosen by the user itself. Now we are at the level when we have to check everything we had proposed as assessment procedures. And for this stage, we have 9 demonstration sites, including residential buildings, but also non-residential buildings. And all these examples will be included in the project just to see if our ideas are correct, and of course how the users will receive and accept all the ideas. Of course, the outcome of such assessment procedures are energy performance certificates. But as I said, we don't assess only the energy consumption. We assess many other aspects. And that's why it's important to give the visualization of every calculation. These are 2 proposals which are not the final ones. The first one on the left side is for the building level, and the second one is for the complex level. And you can see that each group of indicators has a special section in our energy performance smart living EPC certificate. So I now say the conclusions and what are the perspectives. So first of all, this project is important because it will support the efforts for reducing overall carbon emissions. Of course, the users can assess how healthy is the building, how efficient, how comfortable is the indoor environment in that building. Then this project is the first one, or among the first ones, trying to propose to European Commission ways of harmonizing the energy performance certificates at European level. It will also give some, let's say, hints in order to compare the maps in different countries. And then it is a question of titling and naming their certificates. In my opinion, and this is a personal opinion, we have to switch from the title of energy performance certificate to a more comprehensive title like building sustainability performance certificate, or even complex sustainability performance certificate, community sustainability performance certificate. So we will assess from an overall point of view the buildings in the future. And this is also important to mention that the project in which we are involved will give us the opportunity to develop at national scale the software used for the energy consumption of buildings. And of course, other outcomes are the articles we will publish in different journals. So I will end my presentation thanking you all for the attention.
Thank you very much for this very interesting presentation. Now we have time maybe for 1 or 2 questions from the audience. Okay, we have 1 question from the audience. Yes?
Thank you very much for your presentation. I would like to ask, I don't know where about the EPBD much, but I want to ask, is this project of like you're doing the project, but this certificate will be mandatory for all the buildings in Europe, or is this like a certain amount of like government, only government buildings is have to follow this certificate, or like you were saying, like these indicator have to mandatory for all the buildings in the EU, or I mean,
yes.
So legislated,
according to EPBD, the energy performance certificates are mandatory for all buildings, of course, according to the case for selling or for reception of the works at the end of the execution stage. But according to our project, these assessments will be, of course, done for all buildings, can be done for all the buildings or complexes of buildings, but this is only a proposal for the future. There will be different outcomes used by the scientists who will be involved in different other projects. And it is also meant to help the experts working for standardization bodies to come with other proposals. And of course, as I said, this is just a proposal for the future. In our opinion, is not enough to assess only the energy consumption. We have to focus also on the comfort in the building. We have to focus also on the environmental impact of buildings. So everything will in fact be beneficial for those targets in 2030 and so on, so 2050.
Okay, thank you very much.
So if there are no further questions, thank you, Professor Lungu. Our next presentation is evaluating smart readiness and energy flexibility in buildings, insight from SRI testing in Slovenia and Croatia, and will be presented by Boris Sučić from Jožef Stefan Institute from Ljubljana. Please.
Thank you very much, Mrs. Chairman. Dear friends, dear colleagues, ladies and gentlemen, I'm really happy to be today with you. And also I would like to use this opportunity to once again thank you very much for your warm hospitality. This is the reason why we are coming here. We feel like home, and this is really highly appreciated by, I think, all the participants. The title of my presentation is Evaluating Smart Readiness and Energy and Flexibility in Buildings. I will give you some insights from Croatia and Slovenia. We have tested the smart readiness indicator in several buildings. You will see many interesting facts. But of course, I will concentrate not to talk much about the EU laws and everything. I will give you the practical insights, how it looks like in our countries. When we started the story about energy performance of building, and also we go beyond not just energy, but also other elements of building performance, we realized there is a lack of data, and energy auditing at that time, 25 years ago, was a logical step forward. And I'm sad to say that after 25 years, we realized again that people are not aware that energy audit can be done, that has to be done by the site visit, proper planning, and all the elements. Many people think that it can be done by phone. You don't even have to visit the building. You can use the Google Maps to do the audit. That is not the way. But also the ultimate goal of whenever you do any kind of analysis is also to provide the useful advices to an end user, identify the opportunities for reducing energy and also improving the comfort living in a building. And that is the reason why we started this story. And also the idea is there is a need for verification of savings and active support to the building operators. The story about smart readiness, it started in 2019. I will tell you my personal opinion. I like it a lot because I'm an electrical engineer. This is the story when electrical engineers decided we want to be part of the building story. So not just mechanical and not just civil engineers, we also wanted to be part of this story. The idea is to assess the building stock and try to get the idea how the building stock can be flexible, and also how to use all the positive elements from the technical building system. The idea is also to analyze the readiness of a building for the implementation of smart technologies. Many people think this is the smart way of selling new things, but it is not. Also, at the moment, the smart readiness indicator is officially tested in 15 EU countries. We are happy in Slovenia that we are doing it through several EU-funded projects. So we are using the lessons learned from those projects. We are using the buildings that we assessed in many different ways also to assess the SRI. The idea in European policies, at the moment, it is not mandatory, it is voluntary. But in European policies, something that is voluntary now in the next 5-10 years will become mandatory. We are also happy that European Commission recognized that calculating SRI for the residential building is not a very smart way of doing it. So things are evolving. The idea is to use the SRI to enable another level of energy services to be deployed. In what is the real world in Slovenia and also in Croatia, many different monitoring systems are installed, but the data is used only for one single purpose. There is no, at least in many buildings, there are no platforms that will collect all the data and use the same data for different purposes. And that is the reason why we concentrate in our testings also to do all the steps from the energy auditing, creating BIM models, analyzing the real data stream, because Slovenia is specific. In our case, you can get the energy performance certificate also for the non-residential building based on operational data, not just calculated, because we were fighting with how to reduce the performance gap. We realized that sometimes calculated energy consumption is very much different from the actual consumption in a building. That was the reason why we introduced several changes in our legislation. This is the reason how it is done, and this is the way how it should be done. You always have to understand the context of the building. And when you are installing energy management system and you are installing smart technologies, you have to understand, for instance, you can do it. I made a mistake in my own institution because we renovated our transformer station and we did it in the most advanced way. Now my electrician is afraid and I have to do his job because he's afraid of all new things that are installed there. And that is the context of energy use in buildings. The guidelines how to do it. Here you can see, of course, you can check in the paper, but what is really important? It is important to connect all the activities that you are doing. Energy audit, energy performance certification, SRI auditing. If you are doing it separately, it will be really costly for the end user. Nobody will pay for it. Today, you know how much is the price for the energy performance certificate. It's not too much money. And if you want to make it even more complicated, then you are risking that nobody will do it. The real idea is to connect all the activities, and then if you are doing energy audit, it is not a problem to calculate the energy performance certificate, and it's not a problem to calculate the SRI, and the end user will have the real value of your calculation. Understanding data patterns. In many cases, we have realized that, for instance, the easiest way is simply to draw here a target line and say this is the single data pattern. But this is the live data from one of our buildings, and it is not a single data pattern. You have this one when the cooling system is not operating. This one when the cooling system and heating systems are operating together, which is not a nice thing to do. And this one is the third data pattern when only the cooling system is operating, and that's a proper data pattern for the cooling. Just to show you what are the value of SRI in Slovenia for the 25 buildings that we analyzed so far. For the 25 buildings, the most modern one, really the most modern building in Slovenia, we get that luck that my colleague is working there, so we had the access to it, and we were able to do the calculation. Has the score 51. In our grading system, 51 means that 51% means that you barely pass the level. So when we told the owner of the building that the most modern building scored 51, he said, don't publish that anywhere. So this is the real situation. The second one, the building number 15 here, scored 38, and that was the building owned by the wealthiest Slovenian guy. And he said, don't publish it anywhere. He's, of course, he's still very proud on his building, but these scores are really low. That motivated us to think about another indicator. I'm also coming from a scientific institution, and we know how to make simple things look very complicated, but we believe that, you can't see the formula here, but you will be able to see it in the paper. But we are comparing actual SRI score with the benchmark score. That means that the best building here that scored 51 is actually the one that is the best one. So we are comparing the 51 with the 51. And that gives us a score of 100. This is the way how this indicator can become dynamic, because when the database will be populated, every new building will be compared with a new benchmark. And of course, not all non-residential buildings are the same. So the schools will be compared with schools, universities with universities, office building with office buildings with office building. This is the way how we can help and also try to make this SRI indicator a living thing, because at the moment we are unable to sell it to anyone. No one wants to buy it. When they see the scores, they said, no, I don't need it. Of course, when you are doing SRI and calculating, you have to be aware that you have to check what are the potential for the flexibility. Always calculate the load factor. This is really important. See how you can adapt, because now we in Slovenia, for instance, we reformed the tariff system for the electricity, and these things can make good money. Of course, these are the measures that we identified through our analysis. They are typical measures for the energy efficiency in buildings. This is also something that can show that SRI, if it is calculated properly, can be the basis for the identification of real energy efficiency measures, and it can help end user to reduce the consumption. These are the results for the three different buildings that two from Slovenia and one from Croatia. We were analyzing in two different ways. First of all, we analyzed the current situation, and then we analyzed the potential for the improvement. Here you can see the difference. The third one, the lowest one, is from Croatia, and you can see the part related with the flexibility and grid services. In Croatia, they don't have a laws that will actually push end users to use the flexibility in buildings. In Slovenia, we have it, and that is the reason why in the implementation of the smart renovation scenario, you can see in the upper part of the slide, you can see that Slovenian buildings can be improved in an economically justifiable to use also the flexibility in buildings. This is the case, for instance, for one of the buildings that we analyzed. We provided our client this kind of calculation, so that he was able to see what he can get from for instance, a modern battery system, how it can be used in his buildings to improve the energy performance. And also, this is the reason why he actually gave us an opportunity to do the calculation, because he wants to see a real impact and the real savings for him. And don't forget, when you are doing it, and measurements without monitoring and targeting are not enough, always ask yourselves how efficiently use your own data, because proposing installation of new sensors, if you already know that nobody is using the already existing sensors, nobody's analyzing the data, that can be costly for the end user, and also that you can jeopardize your reputation. Always see what you get, what you already have. Try to analyze that data that you already have, and try to not use it just for the single purpose. Try to use it for different purposes. My conclusion and advice for all of you: be demanding in the implementation of energy efficiency measures and demand sustainable solution. Our story definitely revealed that ESCO companies that are interested to implement flexibility services like the SRI. Of course, the major problem and the major challenge is public perception of SRI as another bureaucratic requirement. We have to try to make it dynamic as possible, and we have to try not to make the same mistakes we did with the EPC, and try to combine the activities, auditing, EPC, SRI. That is the only way how the final price for the final user will not be too high, and they will be happy and ready to use it. That will be it from my side. Thank you very much for your attention.
Thank you very much. Do we have any questions, please? Yes, please.
Thank you very much for an excellent presentation. I'm fascinated to try and understand that the building that did the best, which got a rating of 51, right?
Yeah.
What was the gap that could have been done to raise the number from 51? And where would you see where it should go to? And are there easy measures if it wants to go from 51? Where does it need to go? And what investment was required? I mean, obviously, it was the most modern building. They're very proud of it. And then to be told they only had a rating of 51%. I know the coefficient brings it up to the best at 100%. But what extra should they have done if they were thinking it better at the time of design or construction or selection of materials? I'm interested whether there was a path forward of how that rating could have increased.
Yeah, for instance, in that building is located in the Alpine space. So the owner of the building, the owner of the building allowed the manual operation of, for instance, of ventilation system, because users like to open the windows because they are in the Alpine space. The outside is fantastic, and that is not very beneficial for the SRI score. The other thing is they have the PV system, but they don't have the battery to balance all the systems. So that and he's thinking about battery, and definitely that will be installed. The story with the ventilation system and another additional sensors related with it, it will not be installed, because he still insists that living in the Alpine space is utilize the benefits of the Alpine space. Also, the parkings at the moment are available for the electric cars, but they are not controlled. And they will install the control system for the parking spaces. So the parking spaces, battery, and the PV that is already installed will be combined in order to balance the system properly. And the third thing that he's planning to do is to upgrade the already existing energy management system, which is today capable to do demand side management, but not providing any information to the end users. So the data from the energy management system is only analyzed by the energy manager at the location. In the future, data will be available at the entrance of the building, and also each user of the building will have a chance to see predefined views on his energy performance, his office, his floor, and other things. These are the things that will be done in that building. And thank you very much for your question. Yes, please.
Yes, thank you very much for the presentation. It was very interesting. And we are struggling with the same type of issues. We are doing performance monitoring on air conditioning refrigeration systems to optimize them. And so we present the efficiencies. And of course, efficiencies can be fairly low. And there is always this psychology in this, because of, I agree with the challenge that if you see that you are fairly low, but at the same time, if you do like you do, you remove a lot of the incentives to try to improve. So, I mean, we try to focus on showing what is good. Yeah. So even 70% compressor efficiency, for example, is very good, but it's not 100%. So there is a danger of this with normalizing it to what is common practice, because you remove the incentive to improve.
Completely agree on that. So yeah, completely agree on that. But we were actually facing with the fact that people were really disappointed with the scores they got. And when you talk with the owner of the building, who invested a lot of money, and explaining him that 38 is okay, it is the hell of a job.
No, I see I mean, we struggle with this all the time, but yeah, maybe it's not good to remove it, to normalize to common practice.
Yeah, agree on that completely. Agree on that completely. What is also interesting for Slovenia and Croatia, and I think it can be applied also in Serbia, the positive jealousy. This kind of normalization can initiate the positive jealousies, because we like to be positively jealous on our neighbors. So when you see other building that is better than us, then you can try to be better than that. Okay, guys, thank you very much for everything.
Okay, so the next presentation will be presented by Botond Fülöp from Budapest University of Technology and Economics from Hungary. The title of the presentation is Preparatory Building Diagnostic Analysis for Energy Refurbishment.
Okay, so welcome everyone, and I'd like to thanks for the opportunity to being here and presenting you. I brought you some slides regarding preparatory building diagnostics analysis for an energy refurbishment. So few things up front. In Hungary, the total final energy consumption, 40% of the total final energy consumption is being used by buildings, and 1/3 of the total final energy consumption is being used by residential buildings. And quantity is not just one issue, or the ineffectiveness of the current building stock, but the other issue, the type of the fuel, that 60% of the energy is what is being used in residential buildings is coming from natural gas, and 30% of the total comes from renewables or biofuels. But firewood in our home falls into this category, so that's a huge part of it. energy refurbishment, especially the deep energy refurbishment in the houses, in the households, would solve the efficiency of the buildings and would lay down the foundation for implementing new building service engineering systems with novel technologies, with more renewables and lower consumption. An average household in Hungary approximately consumes 20% more energy than in the EU, and large portion of it goes for space heating, only for space heating. To meet the targets, which is climate neutrality by 2050, we had to keep to roughly 3% of renovation rate annually. Currently, this rate is around 0.5%. To justify energy refurbishment or large-scale energy refurbishment, there were some surveys made involving a lot of buildings. This one is from a national building energetic strategy involving 21,000 residential buildings. We have our buildings mostly consist of panel buildings. Half of them were at some level renovated. More surveys involving even a microcensus showed that under 10 years, more than 600,000 heating system replacement happened. So concluding, all these little surveys showed that there is major potential for reducing consumption, of course. And what is more important, that occupants mainly believe in this process, and they seek the opportunities and would invest more if there were more subsidies, more incentives. And according to the latest NECP reported, we have 4.6 million households, and more than half of it must be renovated and must undergo some kind of renovation in the near future to meet our targets, which is roughly a 90% energy reduction in the residential sector. So we started to deal with one fraction of the problem, which is a residential building in the 8th district. This one consists of roughly 100 social housing units. It has total 4 stories. And the floor plan shows how small and packed these apartments are. Usually, a net floor area is around 30-40 square meters. They have only one facade facing towards the outside. Most of them faces towards the inner courtyard. So these are maintained by the municipality and resided by mainly it was rented out to disadvantaged tenants who are in need, have no financial income or small financial income. So we started to assemble a renovation scenario, make some surveys, and measured characteristics of the building. Some of them, we started with measuring U value of one facade wall by installing a heat flux meter and calculating the U value of it. It came with certain conditions. It had to be done during the winter. Like a certain difference had to be kept between the inner and outer temperature, avoiding, of course, thermal bridges, and try to find a heterogeneous wall section. These are the results of the measured temperature. Red one shows the inner temperature, lower, the blue one, the outer temperature. The sudden drops in the curves indicates that the tenant was quite punctual regarding natural ventilation. These were the calculated U values. The blue one is the instantaneous, and the red one is the average value. It came out that roughly 50 centimeters brick wall has a performance of around 1 watt per square meter Kelvin. We also gathered one brick and took into the laboratory and cut, grinded, and measured the characteristics. Physical and characterization was measured in a climatic chamber, and thermal conductivity with modified transient plane source method. On the left, you can see that from this arrow, usually they stamped, every brickwork company stamped their bricks in their unique shape or logo. These were the equipment that were used. And then we got into multiple apartments and tried to find the weak points of this residential block, and photographed with a thermal camera possible or potential thermal bridges, slabs, and floors. It turned out that in units like this, usually we have a lot of unoccupied residential units, and water infiltration from the basement causes problems, and also deteriorated fenestration. These all causes like major heat losses and discomfort for the tenants. So as a conclusion, if we want to provide with a holistic renovation scenario to the municipality or some stakeholders, it has to be well researched and supported, all these bases. Thank you for the attention.
And I have a question.
Yeah, okay.
Are there any fiscal incentives, and if there are any, are they easy to access in order to do these kinds of renovations in Hungary, or are they also costly to prepare in terms of documentations and costs?
Incentives on what level?
Fiscal incentives.
It's really hard topic because usually these people, of course, don't have let's say, don't have much voice regarding this, and they usually pay their utilities. In some cases, if they are really poor or disadvantaged, some of the utility fees are paid by the municipality. Maybe that pointing out that using less energy is better for the district, for the municipality.
Is the only
I think, yeah, because usually they pay for their utility fees, and in some cases it's not even like in a way we used to pay our bills. They have like they have to buy their electricity or gas in advance, and after they can use it. So this is well reflected in their energy consumption as well.
Okay, thank you.
Welcome.
Okay, thank you very much. Do we have some maybe other question or? No, if not, then we're going to do our next presentation. It's titled Development of Energy and Carbon Neutral Warehouse and Distribution Centers Using Building Simulations, authored by Norbert Harmathy and Anna Bence from the Budapest University of Technology and Economics, and it is going to be presented by Mr. Norbert Harmathy.
Thank you. And thank you once again for the opportunity. This is my, well, probably the third or fourth time at this conference. So it's always a great pleasure to present here what we do and discuss about energy efficiency and green building technology. So concerning this topic, what I would like to show you now, this is a building which we worked on for, well, let's say, around 2 years. And usually the green building is widespread in the commercial sector and in the hospitality sector. But the warehouse and the distribution sector was always a bit left aside because these buildings were not that important within the green framework. So now it turns out that these buildings are becoming more and more important, and I would like to show you one of them, where we gained BREEAM Excellent International Green Building Certification. And the investor had the goal to develop a center which is carbon and energy neutral. So if we start from the already known 40% responsibility of the buildings in the greenhouse gas emission and in the energy consumption, we have to look a bit deeper inside and see what's the operational carbon problem within the buildings. And it turns out that 27% is dedicated to the operational energy and carbon, which means that the 27% has the highest potential of reduction, because we cannot help in that case with the embodied carbon. So if you look at the operational carbon, and if we divide what does the operational carbon consist of, it consists of the HVAC system, lighting, equipment, elevators, domestic hot water, and other like receptacle equipment. Now, concerning the highest amount of carbon emission, that comes from the HVAC system and lighting, which is around 65%. So that has the highest potential. The investor's goal, the Hello Parks Logistic and Warehouse and Distribution Center, their goal was to gain BREEAM, the Building Research Establishment Environmental Assessment Methodology, for all of their buildings. And they, well, so far have developed around 10 logistic centers. I will show one of those 10 logistic centers. And in this logistic center, we managed to get the BREEAM excellent level of certification, which means that the building is green. It's developed in a manner that for a long term, it will use less energy, it will have less carbon emission, and the investor's goal was to make a carbon neutral building. So the following goals I would refer to. First of all, we had to meet long-term environmental requirements. We had to develop an energy and operational carbon neutral warehouse and distribution center. And all of this started with a feasibility study where we studied all the renewable and low carbon energy sources applicable for the building. So we helped the investor during the decision-making process concerning the building design, concerning HVAC system, and concerning the investment costs. So here you can see the building. The building was handed over 2 months ago, so somewhere in October. So the building now is fully functional, and it consists of 5 separate rental areas, as you can see on the image above. The separate rental areas consist of office spaces for each rental area, and the building is around 25,000 square meters. Concerning the conceptual and feasibility study, we analyzed 4 different types of systems, and we always compared these systems to the first one, which is the notional system, which is the minimum requirement of the energy efficiency regulation in Hungary, which is equal to the energy efficiency regulation in the European Union. So the first system was a notional system consisting of gas and electricity. Concerning the gas system, the building then has a condensing gas boiler with higher efficiency, which is used for warehouse purposes to heat the warehouse and heat the offices. And we also use air conditioning for cooling of the office blocks with 65% of heat recovery. The second proposed system was the system which is usually used in warehouses, which are energy efficient at the moment. And the second system is a fully electric system consisting of air source heat pumps. And usually this system is accepted by all investors within the warehouse and distribution center industry. The third system is an upgraded system where we also have a heat pump, but with variable refrigerant flow, so VRF system, which is with higher efficiency. And we have additional mono split ACs, but here the heat recovery is higher, 83%. So this is an upgraded, better system compared to the usually used one. And then we have the fourth system, which will bring our building to a carbon neutrality. Then we added to the third system on-site generated electricity with photovoltaic panels. So the building is covered in PV panels. And I will immediately turn to the results. The results were the following. So we look at the notional system where we have condensing gas boiler and electricity. It's around, well, 1,300 megawatt hours on annual basis. And if you look at the second system in the third column, the second system is 520 megawatt hours. So immediately you see a huge difference if you compare it to the notional. So it's more than half of the energy reduction, and usually that system is accepted. Now, if you look at the third system, where we have the VRF system, which is more efficient, then we can make it even half of the energy consumption, so 256 megawatt hours. And finally, if we turn to the upgraded on-site electricity generation system, then we can even export 244 megawatt hours of produced electricity to the grid. Now, the thing is that the electricity which is produced can also be used for other purposes. For example, powering electric vehicles, or probably in the future, powering electric trucks, electric transportation. So system 4 with the solar panels, we decided to use solar panels with a peak of 468 kilowatt peak. So the estimated annual energy production will be around 500 megawatt hours, which is double the usage of the distribution center. So if we look at the operational energy reduction, we can manage to reduce the energy demand of the building to zero, which means that the utility bill then will be zero, so we can even sell energy from the distribution center. And the idea is that all 10 distribution centers at the moment will be positive energy producers. So the thing is, if we look at here, for example, the energy reduction compared to the notional system in system 2 was 60%, and usually that's always accepted, and usually then the investor is satisfied. If we look at system 3, we can reduce it by 80%, and with system 4, we can reduce it to 100% on an annual basis. And as I mentioned, in the future, it will be used for powering even electric trucks. At the moment, it's powering electric vehicles. So this additional energy is stored in batteries, and the company Hello Parts can use it for vehicles. But now comes the funny thing, that if you look at carbon, and usually we don't even always look at carbon, we look at only energy. But now if you look at carbon, it comes out completely different. If you look at the first system, the notional system, where we have gas and electricity, the operational carbon emission on annual basis, if I look at the latest row, the annual carbon emission per system in kilograms per CO2 on annual basis is 264 tons of CO2 on annual basis. But if I look at the second system, where I had 60% of energy reduction, I actually have almost double the carbon emission, 473 tons of carbon on annual basis. Why is that? Well, it comes from the electricity producer. So if in a country you don't have a lot of renewable energy for electricity production, then your carbon emission is extremely high if you use only electric powered systems. So it turns out that I can reduce the energy by 60%, but I will have double the carbon. So the equation doesn't come out efficient. So it's not a good building. It emits a lot of energy. Maybe the bill is smaller, but the energy is the carbon emission is extremely high. If I look at the third system, where I have a VRF, a super efficient system, I get the same carbon almost as I got in the notional building. With less energy, 80% less energy consumption. However, the carbon is very similar. What's the only solution in this case? The only solution in this case, if the provider doesn't provide low or zero carbon energy, The only solution is to implement PV panels, and the PV panel can contribute to these carbon emission savings. So if I look at the operational carbon, first of all, if I compare it with the notional system, system 2 had 80%, 79% worse results compared to the notional case. The third system, the VRF system, which is a lot more expensive, uses a lot more energy, but emits only 12% less carbon. And the final system, where we have a completely integrated PV on the roof construction, then we can assess this 100% of reduction, plus charge the electric vehicles, which is a positive feedback. So thank you very much for the attention. If you have any questions, I'm here to answer them.
Very interesting presentation. Thank you for all details you gave us. I have one question. So according to EPBD and to national laws transposing EPBD, the new buildings must be nZEB buildings. And I wonder why you didn't mention this, let's say, rule for new buildings in your presentation. What's the reason behind? Because you mentioned BREEAM certification scheme, which is a commercial one, is a voluntary certification scheme. Why didn't you refer to this rule of nZEB?
The nZEB is actually the second system which is usually used, the complete heat pump system. So it's used for heating and cooling as well on an annual basis, that reaches the nZEB requirements. So the nZEB requirements can be reached by the second system. That's why the second system is the most widespread, unfortunately. But then here it turns out that if we look at details in the carbon, and if you look at more details on a 50-year operation of the building, then it turns out that it's inevitable to integrate renewable energy production, not only to reduce energy, but to cover that carbon emission with renewable sources.
Okay, thank you.
I have also one question, which is very similar to this question that Professor Catalin asked you. In Hungary, do you have obligatory process of energy performance certification for this type of buildings, right? Like warehouses? Because in Serbia, they are excluded from the obligatory certification.
Well, it depends from the temperature inside the warehouse. So the offices have to be certified. So we always, with the BREEAM certification, it's obligatory to give an energetic passport, so-called, energetski pasoš. So the thing is that we have to have an energy certificate for the office spaces. That's mandatory. And if in the warehouse, the temperature is higher than 12 degrees, if it's tempered to 12 degrees, then you don't need a certification. But if in the warehouse it's higher, let's say 16 or 18 degrees, then you must have an energy certificate. So concerning these buildings, it will depend in the lease agreement. So depending what will be stored in the warehouse, if the goods require higher temperatures, then we must have an energy certificate. That can be done additionally. So at the moment, it will be connected to the lease agreement, but the building is constructed, it's insulated, so actually it's prepared to apply for an energy certificate.
Thank you very much.
Thank you very much. It was very interesting. Thank you. Are there any further questions? Lots of them, actually. Great.
Okay. The gentleman here.
Oh,
raise his hand.
Thank you very much. Really interesting presentation. Just two questions. One is the financial costs and return on investment, which is a fairly obvious one, and the funding model that goes with that, the government incentives, the return back to the grid of your extra generation from PV. But I'm also interested in the embodied carbon, because you're now putting in an additional investment facility, which now has an embodied carbon footprint. So my second question, which is probably my most important one, is the life cycle cost analysis over the lifetime of the facility in terms of the overall footprint and impact. Thank you.
Okay, thank you. Well, I will start with the second question concerning the life cycle analysis and the LCA and the LCC. Since it's a BREEAM certification, it's mandatory to have an LCA and LCC analysis and to prove that the building is minimum 10% better compared to the standards. Concerning this building, we used a lot of recycled materials, starting from the steel, concrete beams, aluminium, glass. So actually the providers for these logistic centers, they are already under contract to provide the materials and construction materials which have EPBD, cradle to cradle, and etc. certifications. So the embodied carbon in this warehouse compared to a traditional warehouse is around 45% lower, because it uses a lot of recycled content. The second question concerning the investment, the cost. Actually, these materials do not cost more. Usually the investment comes out the same. The only additional cost was the PV integration, but that cost will come back through the lease agreement, because in order to lease space in this warehouse and distribution centers is a bit higher compared to a traditional warehouse, because it guarantees zero energy usage. So, and the investors and renters, they if they don't want to pay any additional costs, they can rent here for a bit higher price. So if they rent for minimum 10 years, then they will have a very good agreement. So actually, I see it generates a lot of positive impact.
Thank you. Since we are a little bit short and on timing, if there is, I saw that there was another question. If it is a very short one, we can take it. Otherwise, we will go. We will move.
The break.
Yeah, after. Okay, thank you.
Okay, thank you.
So thank you very much. We'll move forward. Our next presentation is optimization of the hotel energy system using a combination of linear programming and multi-criteria optimization, presented by Draško Kovač from University of Montenegro, Faculty of Maritime Studies, Kotor. Thank you very much. The floor is yours.
Thank you. Ja ću dati doprinos da budemo u domenu prezentacija svakog rada, pa ću se potruditi da bude moja prezentacija vrlo koncizna i jasna i da traje u okviru predviđenog.
Translation is available if you need.
Thank you. Rad koji smo uradili profesor Aleksandar Anđelković i ja bavi se optimizacijom energetskog sistema hotela na južnom Jadranu. Sam porast turističkog sektora, posebno hotelske industrije i hotela sa povećanjem i potrošnje energije, kao i ekološki uslovi, udobnost gostiju nameću menadžmentu svakog hotela da se posveti i racionalizaciji energije, racionalizaciji sve potrošnje kompletnog, a posebno u ovom dijelu potrošnje energije u samom hotelu. Svaki hotel ima konzumente mimo gostiju hotela, međutim mi ćemo se ovdje baviti jednom hotelu, primjer hotela na južnom Jadranu, na Crnogorskom primorju. Metodologija koja je ovdje primijenjena bavi se optimizacijom energetskog sistema kroz dvostepeni prikaz linearnom programiranju u prvom dijelu i u drugom dijelu metodama više kriterijumske optimizacije kao što su Pareto analiza i Promete 2 metoda. Zašto je ovo važno? Važno je u cilju smanjenja potrošnje energije, povećanja energetske efikasnosti i promociji korištenja obnovljivih izvora energije. U ovoj studiji slučaja, kao što sam rekao, razmatramo hotel koji je po kategorizaciji spada u velike hotele. Inače se u turizmu na Mediteranu hoteli rangiraju do 50 soba, mali hoteli, srednji od 50 do 150 i preko 150 soba kao veliki hoteli. Razmatra se hotel u Bečićima koji ima energetski sistem sastoji se od električne energije iz mreže koristi kotao na gas za grijanje, solarne fotonaponske panele za električnu energiju, solarne kolektore za toplotnu energiju i toplotne pumpe. Hotel radi tokom cijelih 12 mjeseci i ukupna površina je oko 15.000 metara kvadratnih, godišnja potrošnja električne energije je 2.800.000 kWh, a toplotne energije oko 3 milijuna kWh. To ako pravimo prosječnu potrošnju po mjesecima, električne energije je nešto oko 7.500 kWh, a toplotne energije oko 8.000 kWh. Kao što sam i rekao, sama optimizacioni model se sastoji iz 2 faze. U prvoj fazi smo radili linearno programiranje gdje smo optimizovali po pojedinačnim kriterijima, a kao ulazne podatke smo radili troškove energije, emisije CO2 i kapacitet izvora energije. Promjenjive su bile električne energije iz mreže, kotlovi na gas, solarni fotonaponski paneli, solarni kolektori i toplotne pumpe. Šta smo imali kao ciljne funkcije? Da minimizujemo troškove energije, da minimizujemo emisije ugljen dioksida i da maksimizujemo korištenje obnovljivih izvora energije. Naravno, kao i svakoj linearnom programiranju i optimizaciji, morali smo imati određene ograničenja. Šta smo imali ograničenje? Ograničenje je da zadovoljimo potrebe za električnom energijom, da zadovoljimo potrebe za toplotnom energijom, kapacitete izvora energije, u prvom smislu misleći na prostorne smještajne kapacitete. I ovdje imamo u fazi 1 linearno programiranje kao dostupni izvori energije. Imali smo cijene iz električne mreže, cijene gasa, cijene su i solarnih panela kao što su trošak i emisije i ujedno pouzdanost. Što se tiče pouzdanosti, to smo uzeli podatke iz tehničkog sektora gdje su nam oni dali svoje viđenje pouzdanosti. Također ograničenja u ovom primjeru. Imali smo solarne panele da maksimalno proizvode kWh na dan oko 5.000, solarni kolektori toplotne energije proizvode maksimalno 4.000, a toplotne pumpe maksimalno 5.000. Smatrali smo da je korištenje električne energije iz elektromreže i gas neograničeno. Rješavanjem ovog problema došli smo do 3, odnosno 4 scenarija. Prvi scenario je rezultat pri minimizaciji troškova, drugi scenario pri minimizaciji emisija CO2, treći je rezultat optimizacije kad maksimalno koristimo obnovljive izvore energije i četvrti scenario smo mi pridodali da bude rezultat optimizacije pri minimizaciji troškova, a da koristimo obnovljive izvore energije više od 30%. Dobijeni rezultati uključuju sve troškove na dan, kao i emisije CO2 i korištenje obnovljivih izvora energije. Nakon postavljanja i određivanja ovih skupa rješenja, a to su scenariji, to se nam služilo kao alternative u drugoj fazi više kriterijumske optimizacije, gdje smo kroz Pareto analizu i Promete metode vršili rangiranje ovih scenarija po nekoliko kriterijuma. Koje smo kriterijume izabrali? Mi smo kriterije izabrali 4 kriterijuma, to su troškovi energije, emisije CO2, pouzdanost snabdijevanja energijom i korištenje obnovljivih izvora. U izboru ovih kriterijuma mi smo se vodili konkretno za ovaj problem, s tim što taj izbor može biti i na druge kriterijume, kao što bilo da je to ekonomskog, ekološkog ili tehničkog dio njihove. Težine smo uzeli na osnovu mišljenja menadžmenta hotela. Naravno, kod težine mi smo radili analizu i mišljenja i eksperata i mišljenja i ostalih. Ispravili smo analizu ne samo na ovom hotelu, nego na hotelu preko 40 uzoraka hotela na Crnogorskom primorju. Izračunavanje unutrašnjih tokova i rangiranje scenarija radili smo pomoću Promete 2 metode i korištenje aplikativnog softvera Visual Promete. Računali smo pozitivan i negativan tok i na kraju smo dobili troškove energije. Radili smo po kriterijima troškove energije, po emisiji CO2, pouzdanost i korištenje obnovljivih izvora energije. Rezultati prve faze, odnosno prvog stepena, gdje smo linearnim programiranjem određivali scenarija, 4 scenarija koje smo dobili smo egzaktne podatke o potrošnji na dan, emisije CO2, obnovljive izvore energije na dan i pouzdanost. Rezultati druge faze rangiranja scenarija korištenjem Visual Promete aplikativnog softvera dobili smo da je po scenarijima, vidite na tabeli ovdje pozitivan i negativan tok same metode Promete i da je prvo u rangiranju tom da je prvo mjesto zauzelo scenario C, da je drugo B, a onda A i D su zauzele malo lošiji scenario. Vizualizacija ovih dobijenih rezultata na lijevom slajdu, na lijevoj slici je prikazana parcijalno rangiranje pomoću Promete 1 metode, a na desnoj slici je prikaz rezultata potpunog rangiranja Promete 2 metode. Također u Gaji i Ravan, ako prikažemo to, vidimo odnos ove najpovoljnije, u stvari izabrane, najbolje rangiranog scenarija, to je scenario C, u odnosu na ostale scenarije. Šta mi možemo ovdje da radimo? Pošto smo, rekao sam, uzeli kriterijume sa težinskim faktorima na osnovu mišljenja menadžmenta hotela, odnosno investitora, mi ovdje sad možemo da uradimo dalje analizu osjetljivosti, da vidimo dokle će da idu ti rezultati. Naravno, s promjenom težina kriterijuma i uvrštavanje još određenih kriterijuma i podkriterijuma, sigurno bismo dobili možda i neke drugačije rezultate. Šta smo mi ovdje na kraj zaključili? Da se scenario C ima najbolji kompromis, scenario B koji minimizira emisiju CO2 pokazuje da je dobro rješenje, a scenario A je pogodan za smanjenje troškova, što će u svakom slučaju hotelijerima vrlo biti interesantno da taj dio. Naravno, znate kako težina tih kriterijuma ne određuje samo i menadžment hotela i vlasnik hotela, nego se određuju i bez obzira na subjektivnost, možemo različitim metodama odrediti i objektivnu vrijednost ovih kriterijuma. Na kraj, prikazana metodologija koja se sastoji iz 2 stepena, su 2 faze linearnog programiranja i više kriterijskim optimizacijenim metodama kao što je Promete, može se primijeni i na drugim hotelima različitog kapaciteta, na drugim lokacijama sa drugačijim energetskim sistemima. Ja sam toliko, pokušao sam da budem...
Hvala vam najlepše, baš ste bili brzi. Da pitam da li ima pitanja. Da li imamo neko pitanje? Do we have any questions? Yes, please.
Ja sam Rade Đukanović iz konsultantske agencije za energetske preglede. Zgrada interesantna je oblast i definitivno pokazuje znači veliki potencijal koji postoji za uštede energije. Nije mi baš najjasnija razlika između scenarija koje ste prikazali. A drugo pitanje je da li ste uzimali stvarnu potrošnju objekta i da li je ona modelirana i da li je modelirana, mislim, potreba zgrade na dinamičkom modelu, mislim, koja zavisi, ima i dnevne dinamike, ima i mesečne dinamike od solarnih opterećenja, pogotovo u Crnoj Gori, kao i sada produkcija solarne energije koja se menja, mislim, i na dnevnom i na mesečnom nivou, akumulacije koje mogu da se ostvare u datim slučajevima, kao i velika dinamika u energiji hlađenja, koja je glavni uzrok elektroenergije. Mislim, verovatno su to možda predlozi za dalje razvoj projekta.
Hvala na pitanjima. U prezentaciji je stavljeno da su dalja istraživanja u tom smislu da se radi dinamički, da je ovo ipak nije obuhvatio dinamičku analizu potrošnje, u stvari korištenja ovih energenata tokom dana. Naravno, svakako bismo radili i sezonalnost. To nije bio obuhvat ovoga rada, a scenarije koje smo dobili smo na osnovu linearnog programiranja, radili smo solver u Excelu, gdje smo na osnovu više iteracija dobili te podatke o potrošnji. Da koristimo podatke iz tehničkog sektora samog hotela i financijskog dijela sektora i u svakom slučaju ti podaci su meni dostupni, a za dalju u svakom slučaju mogu vam i prezentovati ako vas nešto interesuje kako smo dobili. Hvala.
Okay, thank you for the answers. The next presentation in line is the one presented by Anton Kirchhoff, entitled Required Limits for nZEB for Different Categories of Buildings. A very interesting topic.
Thank you for this introduction. First of all, I'd like to say that it's a pleasure to be a part of the 55th edition of this great Congress. As I was introduced, my name is Anton Kerchov. I come from the Faculty of Mechanical Engineering of the University of Belgrade. And on behalf of all authors, I'm going to present the paper which will require limits for nZEB for different categories of buildings. This presentation will consist of 5 main sections. The purpose of the introduction is to give better insight of the topic of the research, while the next subsection will provide a short overview of the existing legislation based on the EPBD in EU countries, with a focus on 3 examples. Next 2 sections will be dedicated to the example of renovation of one existing building in the Republic of Serbia with the aim of achieving nZEB. And finally, in the end, all the drawn conclusions are going to be summarized. Buildings are among the biggest energy consumers, and due to the necessity of decreasing of buildings' energy consumption, EU has adopted revised EPBD, which entered the force in May this year. One of the major goals of this EPBD is to reduce the greenhouse emission by 60% by 2030 in comparison to 2015. At the same time, by 2050, the building stock should be highly energy efficient and decarbonized to the level of zero emission building concept. Bearing in mind that according to EPBD, nearly 75% of buildings are energy inefficient, EU countries were to establish their legislation in line with EPBD in order to achieve EPBD target goals. And the Republic of Serbia, being a country on European road as well, should also establish its own legislation that is not only in line with the EPBD, but also should consider the best practices of EU countries that have their legislation established already. With that being said, the numerous EU countries have already established their requirements for achieving nZEB concept. And these requirements are obviously in line with EPBD, but also with their national regulations. These requirements can be different for different building categories. They can be different for new and existing buildings, and they are also different. They're also adapted for each country's specific climate and type of the building stock. The first example is the Republic of Croatia, whose criteria on achieving nZEB is different for different building categories and different in 2 different climates. As it can be seen in the presented table, the maximum values of annual primary energy are different for 9 different building categories, and they're also different for coastal and continental climate. The Austrian methodology, on the other hand, provides slightly simpler criteria, dividing buildings in only on residential and non-residential buildings, with different maximum primary energy values for new and existing buildings. Netherlands methodology, in accordance with the Netherlands methodology, maximum annual primary energy values are defined for different building categories, and this methodology also introduces the required energy obtained for the renewable energy sources. Within this research, the possibility of achieving the nZEB level in the Republic of Serbia is investigated through an example of one existing residential building renovation, with obviously the aim of achieving the nZEB level. The model building is located in the city of Niš in the Republic of Serbia. This building has heated area of heated space around 800 square meters, and U values for this building are not calculated. Instead, in order to generalize the obtained results, they are adopted on the basis of the national typology of residential building in Serbia, so that they correspond with as many buildings possible that belong to the same time period, which is from 1919 to 1945. All the calculations necessary for obtaining relevant results are performed on the basis of the Serbian rulebook on energy efficiency of buildings. However, since this rulebook does not provide any requirements, it does not provide any requirements for the achieving nZEB level, these reference criteria are adopted from the Croatian methodology for continental climate, bearing in mind that it is geographically and also in terms of the building stock, very close to the Republic of Serbia. For the purpose of this study, the renovation of the building implies the implementation of 3 different sets of energy efficiency enhancement measures. They're denoted as case 1, case 2, and case 3, and with case 0 denoting the building's existing state. All of the measures, all the 3 sets of measures imply the replacement of the district heating on fossil fuels as a heating energy source, with the biomass boiler as a renewable energy source. And case 1 implies also the installation of all non-transparent elements of the building's thermal envelope, while the case 2 only implies the replacing old wooden windows of the building with PVC ones with low emissivity glass. And finally, case 3 implies all the measures implied by case 1 and case 2 together. As it can be seen on this figure, which presents the results obtained by the calculation, by implementing the energy efficiency measures performed by this study, it is possible to achieve significant savings in the annual primary energy, which can be from 85% to 88%, depending on the observed case. Also, the implementation of proposed energy efficiency enhancement measures results with meeting the criteria set by nZEB criteria set by the Croatian methodology. It refers to the case 1 and case 3. In case 2, it doesn't actually meet those criteria. It should be noted that Austrian and the methodology from Netherlands criteria are a little bit more strict, so none of these observed cases meet the criteria from those two methodologies. So only from Croatian one for the continental climate. Similarly to the annual primary energy, by implementing the measures proposed by this study, it is possible to reduce the annual CO2 emission by a significant amount. And in this case, actually in all three cases, is around 83%, which shows the impact on a renewable energy source, replacing the district heating with a renewable energy source in terms of biomass boiler. At the same time, the payback period is 8 years in case 3, and this period of 8 years may not be acceptable to most of the investors. However, with governmental support through, for example, some instances, it is possible to reduce this payback period to 5 years or less, and thus becoming a short-term payback period, and considering this as a cost-effective and energy-efficient solution at the same time. So looking at the results obtained by the renovation of this existing building in the Republic of Serbia, it is possible to conclude that it is possible to significantly reduce both annual primary energy and annual CO2 emission, while at the same time meeting the nZEB criteria by some of the EU countries. Also, the payback period is 8 years, but it is possible through some sort of governmental support or the support of ESCO companies to reduce this period and to make it 5 years or less, which would be acceptable by investors. This study shows that it is possible, and thus it is crucial to establish achievable nZEB requirements for the future national regulations, because if these ambitions are too high and the targets are unreachable in those contexts, it is possible to lead to heavy expenses through investment and to set additional burden to nZEB tradition of countries who are in their development process. Thank you for your attention.
I'm Rade Đukanović again. Thank you for a very nice presentation and a very important topic for us on improving current calculation methodology for building certification, which include only heating to what is on European level for cooling, for lighting, and for all the systems and generation, and achieving net zero building. The main issue I see is methodology. And I have also tried to apply Croatian methodology, and I saw that there is a difference. Even the conditions are similar in calculation, the heating energy by our regulation and softwares and with the Croatians. So it was not fully comparable. And when evaluating cooling energy methodology, I found that it is very underestimated, particularly for buildings that have HVAC systems compared to any more complex or detailed analysis. So I think that we really need to establish the methodology that would evaluate the energy consumptions in Serbia in a good quality. And also it has to include the cost-benefit analysis, economic, for evaluating different systems. I mean, the heat pumps technology, the PV, and everything else, which is applied in other countries and is different for different countries. But I mean, it's very good that we are starting to go in this direction with your work. Okay, thank you.
Okay, thank you for your comment. Thank you very much for your presentation. The idea was to highlight this topic because in Serbia, our government is currently working on harmonization with European standards. So that was the main idea. So if we don't have another question, then we can finish with our presentation titled An Overview of Passive Cooling Techniques Using Phase Change Materials for Photovoltaic Panels, Focus on Numerical Simulation, authored by Ivan Ćorić, Sandro Nižetić, Mišo Jurčević, Jelena Bošnjak, Duje Čoko, Muslo Marici, and Agis Papadopoulos. The presentation is going to be given by colleague Ivan Ćorić.
Thank you. Hello, everybody. My name is Ivan Ćorić. I'm a PhD student and faculty of Electrical Engineering, Mechanical Engineering, and Naval Architecture in Split. Today, there is a lot of talk about green transition, which refers to the global shift towards more sustainable and environmentally friendly energy systems. This transition is crucial for according climate change. The global green transition is rapidly progressive. So in 2023, the share of wind and solar energy in global electricity increased from 10 to 12%, with over more than 500 gigawatts of renewable energy sources added. In this transition, photovoltaic technology is play a crucial role, converting directly solar power into electricity. One of the main problem of photovoltaic system is that higher PV cell temperature reduces both power output and efficiency. To address this issue, there are used several cooling methods. Active methods involve external energy input, while passive methods rely on natural process, such as utilizing ambient air, employing natural convection mechanism, or integrating PCM storage beneath PV panels for cooling purpose. Our focus was on PCM. So this is a review paper. Our analysis focus on research conducted over the last 5 years. We use Scopus database for our literature search, applying keywords such as photovoltaic, PV, passive cooling, phase change materials, PCM, and numerical. This was our first table. On this table, we present PCM used in articles along with their properties such as melting range, density, thermal conductivity, and other properties that require for numerical simulation. We noticed some disadvantages from this. As seen in the table, some properties are missing. Also, in the work by Jurčević and associations, it was shown that manufacturer database are unreliable. So it is recommended to measure properties of PCMs directly. And also, when we're discussing about PCMs, it is important, or this is recommended, to refer to the melting range rather than melting point. We can see that on this picture. Also, for example, pork fat, what is one organic PCM, melting start at 5 degrees and end on 44, 45 degrees, what is huge melting range, not melting point. This slide presents different PV PCM configurations. We have one PCM layer or two or more PCM layers. Also, we have PCM in pipes and PCM in porous chamber. Also, PCM can be single or with additives like nano or metal nanoparticles. Numerical simulations are essential for accurate performance prediction, optimization, and cost-effective pre-testing before experimental validation. In numerical simulation, there are different modeling methods taking into various boundary conditions such as ambient temperature, solar radiation, wind speed, convection coefficients. In terms of optimization, numerical simulation allows adjustment in the following area: tilt angle, thickness of PCM layer, material selection for encapsulation, and number of pipes. In this following table, we can see numerical results focus on temperature reduction with corresponding power output and efficiency increase. Also, we see from this table some gaps in literature. First is a lack of data. Most studies focus on temperature reduction, neglecting power output and efficiency improvements. Also, most of them reporting averages instead maximum, reporting maximum instead averages values. That is, it's better to reporting averages because it provide a better understanding of system behavior. One more gaps is that lack of key data of materials such as material of PCM encapsulation. And just few studies include cost-benefits analysis, crucial for evaluating reward feasibility, that is economic analysis. And to conclude, solar energy is a key renewable resource for sustainable energy system. Overheating is a major challenge for PV systems. The integration of PC materials scientifically improves PV system performance through enhanced temperature regulation, and numerical analysis play a vital role in the optimizing PCM. Looking overhead, there is some important direction for future direction. There is a need for comprehensive economic analysis of PVC systems. More comprehensive data on PC material properties is essential for accurate simulation and reproducibility. And future models should account for dynamic environmental conditions such as solar radiation, wind speed, tilt angle, for more realistic simulation, and future research should integrate economic analysis. This work was supported by Croatia Science Foundation, and thank you for your attention.
Thank you very much for this interesting presentation. Is there maybe any question from the audience? From the chairman? No. Thank you very much again. At the end of this session, I would like to thank you, first of all, to our chairman, and then to all of you, of course, for participating in this very interesting and fruitful session. And thank you. Have a nice day. And please join us together on the next session, which will start very soon. Thank you very much.